everybody. Good to see you. I'm Kathi Fisler. I'm from Brown University. Sorry, I was just adjusting to the way all this was coming across on my screen here. Much of what I'm talking about tonight is joint work that I've done with Shriram Krishnamurthy, who's also a faculty member at Brown. I am a professor by background, so I am more than used to questions while I'm talking. So please feel free to hop in and throw questions into the chat. I have it up, and we'll get as far as we get as the discussion warrants. So to start, a little bit about myself. I am a professor of computer science at Brown. I also head the undergraduate studies program, and I'm the faculty advisor for our socially responsible computing initiative. And all of these are going to matter in the design of the course that I'm going to be talking about. I've been teaching first-year computing and informatics for 25 years. I am a functional first person at heart. I have taught second semester computer science in Scala. I absolutely love Scala. In that position, I like the blend of the object-oriented and the functional. So even though I'm not using Scala in this particular course I'm going to talk about, I will come back to the end about where I really see things like Scala fitting in and kind of the mindset and the approach that's there. I'm also a researcher in computing education, so I focus a lot on how people learn and use formal systems. So a lot of my work is looking at the intersection of programming languages, formal methods, and computer science education. And I've done a lot of work in K-12 outreach, which has also informed some of this work. So one of the pressures that I'm seeing, at least in the US context, on a computing science curriculum is we have a strong tech economy, which is bringing many more students into our departments wanting to do well in intro courses. We have concerns about diversity in tech. We're worried about societal impacts of algorithmic decision-making. Data science is becoming very much more popular. And all of this is putting pressure on what goes on in an intro computer science course, looking towards, say, a computer science major. And what I really set out to do when we were set out on this project was to think about centralizing data as a way to think about introducing computing in a way that could lead into CS data structures, but while also making a meaningful introductory course for students who were thinking about data in the world, not just data because I want to maybe be a computer scientist. I want to leverage ideas of data engineering to motivate some of the standard concepts of intro computing, like functions and computational ideas. And I want to be able to teach social impacts embedded within the technical context of the problems that we're working on in this approach. So what does this look like concretely to centralize data in introductory computing? So when I think about this, I think there are many different forms of intro that are common in different places. So there is there's like the imperative intro where you start with numbers and variables and assignment statements and conditionals. And at some point you get to arrays and lists. And that style of curriculum is emphasizing control. It's not emphasizing data. There's the object-oriented algorithmics approach, which I understand is more popular in Europe. And that's going to start with classes, objects, conditional, and loops. And then arrays and lists come in kind of as your first data structure. And then finally, there's your functional intro, which might start with functions, conditionals, lists, recursion, then into higher order functions. And that's going to put its emphasis on traversing data structures. Okay, so all of these are ways to think about going about intro programming. And I really want to pose a question for us, which is, what if two-dimensional tables instead were students' first data structure? Okay, because I think there's an interesting question there about how this would change the way we think about doing this kind of work. So what do I mean by that? So what's on the slide here is a sample table, which in fact I used in class just this morning. And so this table is showing an example of broken data that might have come in on a Google form or something like that. So why would this be a compelling place from which to start teaching people about computer science? Well, I'd argue in part that we have an authenticity perspective for students. Okay. There's data that's in a format they're familiar with. Students have seen spreadsheets. Okay. They know what those things are. They can work with data from many different domains. Depending on whether we're doing, we could do a healthcare data set or another kind of data set. And we can use computation to answer questions that are meaningful for students. Now, compare that to some of what some of us have been confronted with when we first took a computer science class. I don't know about you. I started with Towers of Hanoi, right? It's not a meaningful kind of question for students coming from the broader world that we are in right now. And I think it's really good for us to think about how to bring intro computing to where our students are. The data science perspective on a table like this says we would look at data through statistics and visualizations and maybe compute some trends. A data engineering perspective would say we'd use a table like this to raise questions such as, how do we identify errors in this data? How do we transform and normalize data for later use? And how do we make repeatable processes so that when next year's data comes in or next month's data comes in, that information is already set up and we can just reuse those processes or those functions again. This also has a lot of opportunity for social impacts. We can explore questions of representation and bias and whatnot if we choose to. So it's all going to be in the choice of the data sets that we're working with. So this is why I think there's going to be a lot of power in us starting with two-dimensional tables as the place that we are fundamentally working. So overall, what are the design goals for this class that I'm been working on? Well, so one of them is to be supportive of students from all across campus, many of whom don't see themselves as CS people or math people. We want to cover sufficient skills so that it's still viable as an introductory computing course. And we want to leave students who stop with this course in a place that they could actually go work on a project with a faculty member in another department. So they could go work with an economics professor or a public policy professor and do something useful with the amount of coding that they have learned. Now, at this point, the question you usually get is, what's the best language for working with tables? Okay. And people throw out all different kinds of ideas. Maybe you want to throw Scala in here. Hang on. You want to step back and ask yourself what in detail we're trying to teach, right? The language should never drive the language should not drive the course. Your learning goals should drive the language. That's something I very strongly have believed in for a long time as an educator. So what does that look like here? Well, so here's a layout of the center column here is the set of topics that are in this course and in the order in which we do them. And I'll give some highlights of this as we go through. On the left are some of the broader software engineering or programming language ideas that we're able to bring in through this. And then on the right are the learning objectives or the narrative about computing that we are trying to bring in as we go through these. So let's just look over this. We start with images, and we want to bring across the idea that information and code have structure. When we go to tables, we want to talk about transforming data and how that's something that you can do through little bits of code. Sometimes we're going to aggregate information, and that's where something like lists come in. Sometimes you run into situations where you need attributes within a column in a data set. And the advantage of being in a programming language is you can do that. Trees are going to bring out that data points can have relationships. State will come in later when we have to update our data sets. And hash tables come in at the very end to talk about efficiency of working with associative data. Okay, so that's the high level view of the outline of this. But let's look at this in a little more detail. So the first programs we write, we do this on day one of the course, is we write functional programs in a language that supports images to build flags. And the lesson we're trying to bring across here is that the structure of the image is mirrored in the structure of this code here. I really think it's helpful to have students realize that computation has structure. Too many students come into programming and they want to read code top to bottom, like a novel, and they don't realize how to navigate a piece of code. So we work with images for the first couple of weeks to try to help them figure out that navigation. Then we start looking at tables. So here's the same table that I showed you before. And now we start learning how to write small functions and small scripts to do very specific table-focused tasks. So for example, we talk about normalizing the values in something like this column D. We deal with capitalization. We deal with spaces, white space that may have spaces, may not have spaces. We deal with isolating individual rows of a table. Maybe we want all rows with a certain discount code. There are all kinds of things that lend themselves to small programming tasks. We can either write these tables manually or we can import them from Google Drive. It all depends on where we are in the curriculum. We do the bulk of our programming learning here in tables. The rest of the course is building on that, inching out what we know in smaller bits. So when we talk about bringing in social impacts, for example, now we might give students a table like this and bring up things like what can get inferred about you, what's metadata, what gets collected about you, how do programs make decisions on things like this. All of these are things we'll talk about in the context of tables. One other thing that I'm very, very big on is talking about testing and validation. I think this has been a travesty of most computer science intro teaching that I've seen, is that we think of testing programs as a topic you get to as a junior or a senior. That's when we really get to software engineering. But if we're being realistic about what our students are doing with what we teach them, lots of students are going off with a semester of programming and building apps and maybe trying to get involved with friends in a startup. They're working on tasks that have critical impacts before they get to the courses where we think we will have prepared them for those things. So I think talking about testing and whether we can trust our code is really something essential for us to do from the very beginning. So among the things that I work with my students on is knowing how to make tests for functions. If you have a large table of data, how do you make a good small version of that data set, 8 to 10 rows, so that you could test your programs and gain some confidence in those before you let it loose on your big data set and try to draw conclusions from it? These are things that don't occur naturally to students that we really need to emphasize. We bring in lists when we want to start doing summary statistics on individual columns. So we might extract a column like you see here on the delivery column. We could plot it in different ways. We might do numerical summary statistics on something like column C, fairly standard sorts of things that you could do. Now, because we've been working with tables, when we get to lists, students are already familiar with common patterns of higher order functions. Table functions in most programming language that support tables have things like filters, form of maps, other kinds of transforms and for eaches. So we're able to make that repeat that practice of using higher order functions on more than one data set. More than one data type. And I find that repetition is a good thing to try to do with students. Then the course gets fun. Well, I think it's been fun before this, but now we really start to get into some more of the fun nuances. What if you need structure to a column? So here, I have a column with names. And maybe I want to deal with first name and last name. Do I want that to be one name column? Do I want that to be two columns? What if I do to support cultures where people have only one name, or where the first names come first and the last names come last? All of these variations start to come up when we really think about having our columns represent the structure of the real world entities and the richness across countries, cultures, and whatnot that we might want to be bringing into our data. If you're not already familiar with these posts that are online, like falsehoods programmers believe about names or about dates, they're great fun because they basically show you all the simple assumptions we might make about how to format names and timestamps and the ways they break in different places. But these are really accessible articles to introductory students, at least, the first several items on them. And by working with tables, we can bring in a natural setting where some of these ideas might apply. The other thing I like about this approach to doing Intro CS is that you get many practical questions about data design and about building real world skills for the kinds of problems you might have wanted to code anyway. So, for example, how do you store lists and structures in CSV files? Those of us who've been at this a while, we have our techniques of doing this, semicolon separated or other kinds of list formatting. Well, these now become tasks we can do with students. And we can work with reading in a CSV file that's semicolon separated and reading that into a list that you embed inside a table, and so on and so forth. So I think you get a lot of mileage in giving students practical tasks for wrangling real world data, using the data types we wanted them to have practice on, but again, in these very authentic kinds of settings. One of the other things I like to give them is then a data set like a genealogical medical history, right? So here we have people and ancestors. And if we ask them to find all of the ancestors that somebody has to maybe track a potential medical condition, what they realize is that tables aren't a very good data structure for hierarchical data. Now, we all know this. We know that you use trees or other kinds of data structures for hierarchy, but students have only really worked with two-dimensional tables and one-dimensional lists. So this is our branching off point to talk about why computer science needs data structures beyond lists and tables. We do some tree-based programming at this point, again, in a functional style, lots of structural recursion, but it all ties in to this data-oriented theme that we've been working with. Up till now, we have done nothing with state. We've had no variables, we've had no assignment statements, but at some point, if we're going to prepare students to go out and work in professional programming environments, they're going to need to have encountered that. So we start first by talking about mutation and update of values in data sets. This is before we get to mutating variables. I think it's much easier to start mutation on components of a structure because you can then, it simplifies the semantic model. the semantic model that one has to think about to do mutation with a structure is actually much easier for students than one based on variables and variable updates. So we work on programs that update data, and eventually we get to hash tables for efficiency purposes. Okay, so this is kind of the high level scope of the course and the sequence of pieces that are in it. So now let's return to which language. Now, when I'm giving this talk in a general audience, not one that's kind of a community organizer in a programming language, the most common answer will be Python for this. Why? Because everybody knows that Python is easy. Everybody knows that Python is the language in which to do data science, unless you're an R programmer, and then you might, think differently. But Python usually wins out in a lot of CS audiences as the easy beginner's language. And we've known that functional programming underlies processing tabular data. Okay, so at least Python gives us that. Okay, but it's not really clear that Python is the place to start. Python is not easy for CS novices, no matter what anybody tries to tell you. For somebody who teaches this stuff and tries to teach students to do interesting things with programming languages early on, white space semantics is a nightmare with novices. They don't yet see structure in code. And white space and indentation only make sense once you can understand that there is actually structure to code. Believe it or not, there are no good beginner IDEs for Python in general, and none of the beginner IDEs that are out there support testing. None of them help students understand the semantics of what's going on in their programs. You can get those features if you go to the professional grade tools, but the professional grade tools are really hard for students to use. So I think Python is still worlds away from having good support for intro students who also want to learn how to program responsibly. The fact that list functions mutate by default causes lots of problems for students because they don't understand mutation. We'd rather them start functionally, get that part of programming right, and teach them to mutate responsibly. There's no abstract data types, which has real limitations for us when we want to talk about structures and columns and things like that. And the Python error messengers are professionals, not beginners. So we use a completely different language. We use a language called Pirate. This is something that we have built in-house in the Computing Ed Research Group at Brown. It's been built to support a number of things, but the course that I'm describing is one of the cases around we've built this language. So it has built-in support for images and tables, like I've shown you. Tables are a first-class data structure in Pirate. There's a Python-esque syntax, so it looks familiar to people who've seen some programming before, and it simplifies the transition to Python later. We're actually doing research studies on that actively, on the transition from this notation over to Python syntax. But so far, it seems fairly smooth from an experience standpoint. It's a functional language with proper abstract data types. So it's got a lot of the kinds of features that Scala users would appreciate. It has an object system, but we don't use it for this level course. It also builds in testing by having us attach tests to functions as students are writing them. We've written a whole collection of papers about different aspects of the pedagogy and the language design. So all of this is research-backed and research-driven. That's a good part of why we do what we're doing. So when I look at the which language, what we are choosing to do is we're in Pirate up through the CS data structures. And then at the point that I want to introduce state, we shift them over to Python. We don't have to shift them to Python, but it's a good point at which to make the break and show them how to transition into Python, into some standard imperative programming idioms, and show them how what they've learned already still carries them over in Python. They can do the functional stuff they've already done, but we also pick up the imperative parts. We assume that the following course will go into objects, privacy, more data structures, algorithms, and all of those topics. So this is kind of the linguistic scope I'm in. Now, where would I see something like Scala? I think you could do a lot of this work in Scala as well. I don't think Scala has the kind of image support that we're working with in Pirate, so that would be a bit of an issue. But the fact that you've got that strong core in Scala means that you can do the rest of this quite nicely in something like Scala. And I think Scala is good for bringing in a lot of the data engineering style ideas. And I think it's really important for us to help students understand that data science is not just about statistics. It is also about managing and maintaining our data and our data processes. So just to step back out and wrap this up, and then I hope we can just open this up for some discussion. Because I know you don't often get education talks in something like this, and it often generates a lot of ideas and questions. Content should come first. Language should come second. I think if you're going to get effective computing education, you need the sequence of the content and skills. You need a language that supports that content and skills. And you need an IDE that reinforces those skills from a learning perspective. And it's not enough to throw like beginner friendly error messages in there. That's a piece of it. But there's a lot of things we've learned over the years about how to take a programming environment and make it grow with the needs of students to avoid them getting overwhelmed or having other things that can convince students to drop out of computer science. Functional first benefits from a lightweight computational semantics, and it has support for testing. If you want to teach testing early, you do not want to be teaching with imperative language constructs, because now you have to think about setup and tear down and all of these other kinds of issues that you have to know how to test for eventually, but not in the first 6 weeks of learning to program. You stay functional, the testing can be lightweight, but you still develop those skills and those ideas with students. Another thing that I want to leave you with is, as more people are thinking about what it means to teach socially responsible computing, many people hear that is we have to be teaching about algorithmic bias and fairness. Those of us with technical backgrounds should also be arguing that we have to include practices like trustworthy computing in what we mean by socially responsible. If we claim that we're being socially responsible in our teaching computing, we should be teaching students how to test, how to make reliable software systems, how to check whether a software system is reliable. There are technical aspects to that discussion as well. And if we can use that as a lever to get more robustness and more testing into early curricula, I say we take it. I mentioned at the beginning that I'm a director of undergrad studies for the Brown Computer Science Department. And I want to focus on a trend that I'm seeing happening. At least in the US, you have many people creating data science majors that are separate from computer science majors. So whereas in a computer science major, you'll do intro programming and data structures, and then you get to databases and some data science later on, a data science major is going to focus on introductory statistics and data scripting, and they'll get to an advanced course on data management. Now, what happens to the student who comes into college, starts one of these, and realizes they're interested in the other one, right? So somebody who starts data science and says, oh, wow, I really like programming. I want to pick up in CS. Or somebody who gets, like 5 courses into a CS major and said, hey, I really like data. I'd rather be over there. the switching costs for students are enormous. And if there's one thing I've learned about most first-year students, is they have no idea what the difference is between computer science and data science. They know that they're both things that have jobs in them, and they think they're important. So what I'm really advocating here is if we could bring more of a data-centric view into our first approach for exposing students to both data science and computer science, we buy students time. We buy students time to understand what these fields are, and then to go on to a second course that goes a little deeper. So the way we actually structure this at Brown is the course I've just described to you is an intro course for both the data science program and the computer science program. And from here, they either go to a second course in the data science or a second course in computer science that focuses more on data structures. We've really, really liked this model. It's given a lot of flexibility to both departments, and it's reduced a lot of the switching costs and confusion on the parts of students. So just as a last slide to kind of wrap up where I'm trying to leave this, I think there are these three areas of computer science, data science, and data engineering. They all have roles to play in modern computing infrastructure. And computer science students are going to need more statistics and data abilities than we've had in earlier generations. I know nobody ever even suggested that I take statistics when I was a computer science undergrad many years ago. Computer science also has the benefit that there's a lot of people thinking about, again, social responsibility and the impacts of what we're doing. Data engineering is interesting because it needs non-trivial CS, but I think it often creeps up on people who started in data science without realizing all of that technology that goes into making their work make sense. And then for people who are starting up in data science, they need the statistics, they need those analytic skills, but they're only going to get them so far. And what I'm claiming is we want to start students in this sweet spot intersection of the three areas. And I'm claiming that that's what this outline that I've presented is trying to do. We have a CACM article from July 2020 that laid out a version of the argument I've given in the talk. We have a textbook that we have written that we use in the corresponding course, which I've linked there. I'm happy to open this up to any discussion people want to have about data science, education, programming languages in this space. This is usually a ripe topic for lots of discussions, and I look forward to questions.
Hey, Kathi, thank you so much for your talk today. We have a couple questions, so let's jump in.
There's a Q&A tab. I'd missed that there was a Q&A tab over there.
That is okay. Our first question, would some kind of Scala supporting notebook system like Jupyter or Polynote fit into this sort of curriculum?
So I don't know Polynote. I suspect you could do something like Jupyter. I personally have not hang on, I'm sorry I'm not looking right. My camera's a little above my laptop screen, so sorry if I look a little off here. I have been very wary of trying to use notebooks myself for my own teaching. I find the fact that you don't actually have a read eval print loop that refreshes, for example, when you make a change to your program, it leads to various kind of dependency errors that are problematic. I have had trouble getting testing to work in the notebooks when I've tried to use them, but I am not, a very experienced user of notebooks. I looked at them once or twice and realized that they were not going to be the kind of IDE that I needed, especially because I really want integrated support for teaching and error systems and tools that help students understand the semantics of the language they're using. And what I mean by that, I spend a lot of time with my students actually drawing out diagrams of the heap contents of memory. This is especially when we get into working with lists and when we get into working with structured tuples and things like that. I think it's really important for students to understand where things like aliases come from, and so that they can avoid some of those problems that could come up when they're learning how to do mutation properly. So I really want to work in environments and languages that give me access to that kind of information. So if that's available in Jupyter style platforms, I think that could work out fine. And I'd be happy to hear experiences of people who try it. Okay, have I looked into
That's
Haskell?
wonderful.
Oh, do you want to read them? Oh, you're going to screen them?
Oh,
Okay.
that's okay. Yeah, the next one up on screen is, do you think any or much of Pirate could be implemented as a kind of DSL in a lower level language, i.e. Scala or Python? Or do you prefer this separate language approach with no host language?
I prefer strong IDEs for working with beginners. And if you're going to embed it in another language, I want to make sure you're going to give me an IDE that I can then use to support working with students. And frankly, one of the reasons we made Pirate is we control the stack, right? We control everything from the error messages to the language features. We have found it really useful, especially as people working in computing education, to be able to instrument the language and run language experiments. We've made various custom versions of Pirate to do studies and to try to build new development tools on how to teach students how to test effectively. So I think we have gotten tremendous benefit out of maintaining our own ecosystem, partly because we are simultaneously doing language research. And, as somebody, I've taught most of my career, I've taught courses that start in one language and migrate into another partway through the sequence. I think if you are designing those transitions well, there's a lot of value in it. So I'm not sure I even see the benefit to necessarily doing this in a host language. So I'd be curious to hear comments about why you see that would be beneficial. And now I'm losing track of what's what in the Q&A, so I think I'll just let you keep
That's
running.
okay. That's okay. Yeah, maybe Ryan or others can include in the chat what their thoughts are on that, and let you go through those as they come in. But our last question that I see at the moment is, have you also looked into Haskell or other functional programming languages?
So I am a racketeer. So I am out of the racket community in doing this work. So sure, we've worked a lot with Racket. Racket has been good for parts of this, but frankly, the parenthetical syntax has been a major stumbling block for having people be comfortable using it. We admit that's been a problem. And what we were trying to do in the design of Pirate, and when I say we, I mean, really, this is the part that Shriram Krishnamurthy has really been the one driving Pirate. So I say we because we're part of the same group, but this is really the work of Shriram and his students, Joe Politz and Ben Lerner. In designing Pirate, the name is suggestive. We stole syntax from Python, Pirate, right? That's where the name comes from. So the idea was to take a syntax that was recognizably close to Python, throw away the warts, like the white space syntax, that are painful for students, build back in the abstract data types, and add on language testing support as an embedded part of the language, and build this up as a good ecosystem for people learning to program. I don't see that. I mean, other functional programming languages don't have that support in them. And again, there's the IDE development work, which takes a huge amount of time. So yeah, I mean, that's been my history looking at this through the perspective of other languages. But I would say that what we've done And Pirate has been heavily influenced by our experience doing this with many other languages. It has a type system which you can use or not. So you can put your types on or not put your types on functions, and we use that to stage students into using types in certain ways.
That's really interesting and fantastic. I don't see any other questions at this time, but I think there are at least a comment in response to what you were asking a bit earlier. So I will let you and,
okay, it's
and
Ryan over there.
the others too.
Ryan, you and I might be the only ones on this channel right now, but I'm enjoying the conversation.
No, but yeah, I think the feedback in a sense is really important, and what you and your colleagues are doing over at Brown is really interesting, and hopefully will help improve the learning experience for so many future software professionals.
Yeah, so Ryan, I mean, so looking at the question of iteration speed, I mean, yeah, we never considered embedding something like this. I mean, it was just, we set this out to be a whole stack development effort because we wanted, when we do curricular work, we do language, IDE, textbook. We always co-design those three pieces because in our experience, that has led to the best results in what we're doing. So yeah, we never even considered it because it wasn't the kind of development work we wanted to do.
Right. Very interesting. Well, I think we are just almost up on time, and there are no more questions, but I want to thank you, Kathi, for being here and taking the time out of your day. I really thoroughly enjoyed your talk, and it looks like Ryan and some others did as well. So thank you so much for being here. And we'll see you again soon.
Great. Thanks very much.
Take care.
Bye-bye.
Fire in retro rock.
Roger, Matt. Ready to eject.